Today we're going to step through the binary hexadecimal number notes and then look at some examples on the binary. It says binary hexadecimal worksheet that's in the Otis lesson along with the notes. Okay, so first off, binary is a number system the same way our decimal number system is. It's just that the base number on which it's based on is 2 as opposed to our decimal system is a base 10. Okay, and so what that means, the base of the number just means that how many possible digits that it has. So like binary only has two different numbers in its system, which are 0 and 1, whereas our decimal system, it has 10 numerals, right? 0 through 9. Okay, thought I had done a pen here, but I didn't. Okay, so this is an example of a binary number that it gives right here. And so it's ones and zeros. And so here, we read it the same way we do a decimal value number, in that the largest place value is the farthest left, the smallest place value is the farthest right. Okay, now there's a couple of little words or vocabulary words that kind of come in, and that's just there sort of for your information. I think nibble and bite are the only two that you might see on the AP exam. I don't remember seeing anything beyond that 4 bits is a nibble and 8 bits is a byte. Okay, and a bit is a binary digit. So like a 1 is a bit or a 0 is a bit. All right, and so down here, right, so how do you know what base the number is? Okay, well, they usually do a subscript right next to the number, like these are, to let you know what it is. And so let's kind of take a look at, so what does that even mean? And I'm gonna break out in a different page here. Okay, so we have a number in, all right, base 10. Okay, so what that means, all right, so say I have 4, let's just do 4. We'll start with 4 place values. So the value of this smallest place value is 10 to the 0, and then this one 10 to the 1, 10 to the 2, 10 to the 3. Okay, and so similarly in base 2 or binary, right, if I have just 4 digits there, this place value is 2 to the 0, this one's 2 to the 1, 2 to the 2, 2 to the 3. All right, that's how number systems work. Okay, so all right, so what does that mean? Well, in base 10, remember I have digits 0 to 9, and then in base 2 I have 0 and 1. All right, so say I have the number 2, 3, 4, 6. All right, 2,346. So what does that mean as far as the magnitude of that number? All right, well, it means I have 2 10 to the thirds, and I have 3 10 to the seconds, and I have 4 10 to the ones, and then I have 6 10 to the 0. Okay, so that's how I get, so 2,000 plus 300 plus 40 plus 6, or 2,346. So that's how that's how our base 10 numbering system works. All right, so for base 2, my digits are only going to be zeros and ones. So if I have 1, 0, 1, 1, for example, okay, so I have 1, 2 to the third. I don't have any 2 to the seconds. I have 1 2 to the 1, and I have 1 2 to the 0, right? So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the second is 4, 2 to the third is 8. So this is going to be 1 times 8 plus 1 times 2 plus 1 times 1, or 8 plus 2 plus 1, which is 11 in base 10. Okay, so that's how, if I have a binary number, I can convert it or see what is its equivalent value in base 10. Okay, so hopefully that kind of helps. So let's go back to our little tutorial here. All right, and it gives kind of another example here, but you can see it goes, and this is using 101 to base 2 and its equivalent value in base 10, and then 101 to base 10 in there, just kind of comparing those two values there. All right, so you do need to be able to go back and forth between decimal and binary, binary to decimal. And then the other number system that we're going to use, but wait, before we get into that, let's talk about, because we're going to get a little deeper into this in the remainder of the course, in that the reason we use binary is because computers are electrical systems, right? And so we need to be able to send an electrical signal that can represent numbers, pixels in an image, letters, okay? And so basically, if we use 0 and 1, and this is, if you enjoy this sort of thing, digital electronics is a great course to take where you actually get to kind of work with these signals. But anyway, so if we have a digital signal, right, it has two states of existence. It has a high and it has a low. Okay, and so usually the low value is a pulse that's like 0 volts, for example, if we want to talk volts. And then a high value, typically, if we're talking about integrated circuit chips, for example, right, it will read a high value, might be usually anything above 3 volts is considered a high value. But the signals they're like this. It's sort of like this square wave in that it has only these two discrete positions that it can be. It's either 0 or it's 1. It's either low or it's high. Okay, so that's why we use binary numbering when we're talking about how computers actually transfer information. Right, everything is represented by a digital or a binary signal. Okay. All right, so we did convert. So here's another example. They do it in kind of a similar way there. All right, now here, converting decimal to binary. So this is kind of cool. So here's your example here, but I'm going to go back to my paper and we'll do. All right, so let's do 230, just to give you another example than the one that's in the document. Okay, so 230 divided by 2 is 115, and my remainder is 0. Then 115 divided by 2 is going to be 56 with a remainder of 1. No, 57, sorry. Try that again. There we go. 57 with a remainder of 1. 57 divided by 2 It's going to be 28 with a remainder of 1. 28 divided by 2 is 14 with a 0 remainder. And 14 divided by 2 is 7 with a 0 remainder. 7 divided by 2 is 3 with the remainder of 1. And then 3 divided by 2 is 1 with a remainder of 1. And 2 goes into 1 0 times with a remainder of 1. All right, so then you get the whole thing on here. Is that it? Yeah. Well, try to make it small enough you can see the whole thing. All right, so we start here at the bottom. And so 1, 1, 1, 0, 0, 1, 1, 0. Okay, so this is my ones place, my 2, 4, 8, 16, 32, 64, 128. Okay, so let's see what we got here. 128 plus 64 plus 32 plus 4 plus 2 gives me 230. Okay, so we worked it up backwards, right? 128 plus 64 plus 32 plus 4 plus 2. And that does equal 230. Okay, so just another example for you of how to do that conversion. Okay, so here it talks about, and as you can kind of see, like we look at this number here, 157, that they wrote in binary, and how many more digits are involved if we're just doing plain binary. And so one of the way that we deal with this is to arrange the binary numbers into groups of 4 bits, right? 4 digits. And then we have another system that we use called hexadecimal. All right. And so hexadecimal is going to have 16. It's a base 16 system. And let me just, you guys can read all that, but I want to go down here just to the table so you can kind of see it, the numbers. So in this table, right, so we know the first 10 of the 16 are going to be 0 through 9, but then we run out of number digits, so then we go to letters. So we go A, B, C, D, E, F to represent the rest of the digits. Okay, so hexadecimal has values from 0 to 15 that can be put in a place value, and it's the value of its places. Okay, so just like what we did before, and we're going to be working in 4-bit segments. So we have 16 to the 0, 16 to the 1, 16 to the 2, 16 to the 3. Right, and so those are, so we have 1, we have 16, and then 16 squared is 256, and 16 cubed is 4096. All right, 1 1 0 1 0 0 1 1. I'm going to do like a long binary string, 1 1 1 1 and 1 0 0 1. Okay, so if it's binary, they're all going to be strung together. But then what we would do is we break them into these 4-bit pieces like this. Okay, so, and again, we have, so if I look at this number here in binary, right, this is going to be 1, 2, 4, 8. Okay, so 8 plus 1, so this is a 9. And then 8, 4, 2, 1. So 8 plus 4 is 12, plus 2 is 14. So that's 15. All right. And again, 8, 4, 2, 1. So this is a 3. All right. And then 1, 2, 4, 8. So in binary, this would be 12, would be 13. Now, however, all right, so hexadecimal, it has a 3, it has a 9, but again, these have to be a single bit, right? So if we look, so 0 through 9 is 10. So when we get to 12, 13, 14, 15, so A, B, C, D, E, F, right? So 0 through 9 are single digits. At 10 is where we get to, we don't run out of single digits. And so 10 is an A. So 15 is going to be, that's going to be an F, right? And 13, that's going to be a D. So in hexadecimal, this binary string, like this binary string here, in hexadecimal would be D3F9. Okay, so you can see it using hex, we can use fewer bits to make larger numbers. Okay, all right, so now let's look at our printout here. Oh, let's go back. Let me add a page. Might need to insert this. Okay, in addition to the divide by 2, there's another way to go from decimal to binary. Okay, and so I'm going to show you this other way because they didn't have it in the tutorial, but for some people that they like, this makes more sense to them. So first off, again, I'm going to start out with our place values that we have here. And so again, this is my 1, my 2, 4, 8, 16. I'm going to keep going. 32, 64, 128, and we'll go to 256. All right. Okay, so say I had, say my number is, well, let's do, how about 401? All right, so what I'm going to do is I'm going to look to see, all right, what is the largest place value that will go into this only once? Okay, well, so it's bigger than 256, and twice 256 is 512, which is higher than that. So 256 only goes in once to 401, okay? So minus 256. That leaves me with, okay, that leaves me with 145, okay? 128 will go into 145 only once. All right, so that's the next highest thing. So 128. And 145 minus 128. Okay, that gets me to 17. All right, so then the next, so 64 doesn't, 32 does not. 16 does. So minus 16. Let me make this a little smaller there. Minus 16, that leaves me 1. So 8 doesn't go into 1. 4 doesn't, 2 doesn't, 1 does. Okay, so now let's double check. So if I add up 256 plus 128 plus 16 plus 1, I get 401. So that's another way that you can, if you want to think about going decimal to binary, that's another way that you can do it. That, I don't know, that seems a little quicker to me, but for some people, the dividing by 2 thing, that makes more sense to them. So there's 2 possibilities there. Okay, so now let's go to our handout here. Okay, so let's just do a couple of these. All right, so I'm going to do it on this page. That makes more sense. 186. Okay, so let me erase these off. All right. Okay, so 186, 128 will go in. So 186 minus 128. So that's a 58. All right, and so the next thing, 64 doesn't, so 32. So that's 26. Okay, so 0. I got 16, which is 10. So 1 at the 16, 1 there at the 8. Gives me 2, so that's 0 and a 1. So minus 2, then I'm down to 0. So it's a 0 there. All right, so 1, 0, 0, 1, 1, 1, 0, 0, 1, 10, 10. So let me go back to our 1, 0, 0, 1, 10, 10. Okay. Let's see. Let's do another one where we're going the other way. So all right, so let's look at this one here. Let's break this out here. I have 1, 0, 1, 1, 1, 0, 1, 0, 0, 1. All right, you start at the least significant digit, right? And so let me make it thinner. So that's a group of 4. There's my next group of 4. And then if you have some left over and you have less than 4, you just add 2 0, or in this case 2 zeros to make it a group of 4. Okay, and remember our 1, 2, 3, 4. That is 1, 2, 4, and 8. Okay, so this is 8 plus 1, so that's 9. This is 8 plus 4 plus 2, so that's 14. And 14 was E. Okay, and then this one would be 2. Okay, so 2E9 would be our base 16. And again, we can check it here with the answer that's over there right at the beginning of the column. All right, let's do one more. Oops, guess I was practicing that before. We'll look at where that comes from. Okay, so let's look at that one. So here I have my hex is 4A. Okay, so remember our place values, right? This is the 1's place, that's the 16's place. So 4 times 16 plus, and A is 10. 10 times 1. So that's going to be 64 plus 10, or 74. And again, so we put 74 is the base 10, which matches we can check our answer there. Okay, so hope this helps. And we'll probably do like a little quiz in a couple of days on your just with the binary, decimal, and hex.